All right. So this section, we're going to talk about the net change theorem and average value. This video in particular will be about average or about the net change theorem. And then the next one we'll talk about average value. So the net change theorem is really just talking about the relationship of the integral to the function. And we know, of course, that the derivative of a function tells the rate of change. And so if we want the net change, which would be based on the rate of change, then we can take the antiderivative and then evaluate at the limits. So this is basically just an application of the fundamental theorem that we've talked about before. So let's look at an example here. Suppose marginal revenue when a company sells Q units of a new product is given by this function here, R prime of Q. Compute and interpret the net change between 2 and 300, or compute this integral. So it's a fairly straightforward antiderivative that we need to get, as long as you've been doing the sections before this. And so we're just going to use the power rule in reverse. So the antiderivative of 26 is 26q. Whoops, that was 0.04 there. And then this would be 0.04q squared, add 1 to the exponent, over 2. And then we'll evaluate these at the limits. And so let's simplify this second term. So 0.04 divided by 2, of course, is 0.02. U squared, evaluated from 200 to 300. And so let's plug those in. And I'll let you do a lot of this calculation. We'll plug in the numbers. Whoops. So we're going to plug in 300 for Q. We're going to get that. We're going to subtract when we plug in 200 for Q. And I'll let you plug all that in the calculator, but we get 1,600, and this would be dollars. So the R is revenue. Revenue is measured in dollars typically. And so this would be $1,600. Now it says interpret. So what does this mean? So the revenue is positive. So we are increasing. So revenue increases $1,600 when production increases. And you would not say by 100, because it depends on the 100 that you would be like, where it depends on the starting point, basically. So you can't just say when production increases by 100 units. You have to say when production increases from 200 to 300 units, because likely if you pick another interval of 100 units, you're going to get a different revenue there. All right, so that is that one. Very straightforward integral, very straightforward idea. And so let's look at something that is maybe intuitive to see. It's not maybe intuitive to figure out initially, but when we talk about, so we have an object moves along a line so that its velocity at time t is given by the velocity function there. Find the displacement. So displacement is how far has an object moved. So in other words, if this is your starting point and it moves like this, it moves like this, it moves like this, and then it comes back around, and then it moves, or it lands right there. So the distance it traveled would be this whole, like how far is this line? The displacement would just be how far is the starting point from the ending point. So you think of it like you're at home, you travel to the grocery store, you travel 1 mile, you travel another half mile back the same path, and then you stop somewhere else a half mile from your house. What's your displacement? Your displacement will be a half mile. Your distance traveled would be 1.5 miles, because you traveled 1 mile to the grocery store, you traveled another half mile back. So displacement is talking about just the net difference, or the net change from the starting points, and then the distance traveled is the total distance. So counting every unit that you have moved. So let's start with part A. And displacement again is just basically like it's the net change. So what was the net change from where you started to where you ended? And so we're just going to integrate the velocity from 1 to 4. And this should be a fairly easy integral to calculate. So use the power rule. The antiderivative of t squared is 1/3 t cubed. Antiderivative of t is 1/2 t squared. Antiderivative of 6 is 6t. And then we're going to evaluate that from 4 to 1. And again, just plug in the upper limit to the function, plug in the lower limit, and then find the difference. And I'll skip plugging the 1 in since we're just going to look at the coefficients anyway. So simplify all that, and we get -9/2 in this case. All right, so in this case, this one, if you start here, you're going to end up over here somewhere. All right, so that's the displacement. Distance is a little bit slightly more involved because now we have to consider changing directions. So if we look at the velocity function, we need to figure out where are we changing directions. So we are going, and this is the derivative of the function that we want. So if we started with the function, the original function, the position function, and took the derivative, we'd get the velocity function. So what we're going to do here is we need to figure out when that position function is changing direction. So we need to set the velocity equal to 0 and get that critical value or the critical values. So we factor that, we get t minus 3, we get t plus 2. So we get t equals 3, t equals -2. We don't need that one because we're only looking from t is between 1 and 4. So we only need the t equals 3. All right, and then we can figure out where this is positive or where it's negative. If you remember from previous videos, when we have a quadratic function, the coefficient is positive. So that quadratic function looks like that. So we're going to be decreasing until we get to the left critical point, and then we're going to be increasing till we get to the right critical point, which would be this one, and then we're going to be decreasing again. So now with that in mind, we are going to integrate the velocity function, but we're going to break it up into 2 pieces. So this piece we are moving this way, and then this piece we're going to be moving that way. So let's do that. And so this function would be, this is our s. So I'm not going to rewrite that, but we're going to call it, this is our s of t. So for the position function, that's the antiderivative of the velocity. So the distance would be the absolute value, and we're just going to find how much distance did we travel in this interval, how much did we travel in this interval. So the absolute value of s of 4 minus s of 3, and then plus absolute value of s of 3 minus s of 1. And again, this is our s. This is the antiderivative of the velocity. So we have the position function s, take the derivative, you get the velocity, take the derivative again, which we don't need in this problem, but take the derivative of the velocity, we get the acceleration. All right, so we are just going to plug in these values in there. And when you do that, we get s of 4 is -32/3. S of 3 is -13.5. So that would be a plus 13.5. And then plus the -13.5. And then minus s of 1 is 37/6. And when we simplify these, we get approximately 10.17. And so that is our distance traveled. So we traveled some distance this way, and then we traveled some distance back this way. The net displacement was -9/2, or -4.5. Total distance traveled was 10.17. All right. So that's how you get the displacement and the distance.